This chapter is called semiconductors, and as the name suggests, a semiconductor is a class of materials which lies somewhere between a conductor and an insulator in terms of its electrical conduction properties. As you all know, insulators are very poor conductors of electricity. Conductors do conduct electricity to a large extent, as the name suggests. Semiconductors would lie somewhere in between. Much of the rapid advance in technology that we saw in the 20th century and immediately thereafter can be traced back to the extensive use made of semiconducting materials. The most famous semiconducting material is, of course, silicon. It's the semiconductor which is the most widely used, and circuits made of silicon and other semiconducting materials called integrated circuits, in which millions of circuits made of the semiconducting material can be placed on an area which is only a few square millimeter. Such integrated circuits are used in our mobile phones and in our computers, just to name two important applications of semiconductors. We must first study the theory of energy bands in solids in order to understand how a semiconductor works. First of all, let us consider a single isolated atom. Every electron contained in that atom has 4 quantum numbers associated with it, and those 4 quantum numbers are, of course, the principal quantum number n, the orbital quantum number L, the magnetic quantum number m, and the spin quantum number s. And the energy of that electron under ordinary circumstances will primarily depend upon its principal quantum number and its orbital quantum number, and it will also depend to a small extent on its spin quantum number. So for example, if I took an electron in this atom whose principal quantum number is equal to 1 and whose orbital quantum number is also equal to 1, so naturally I am talking about an electron in the 1s orbital, and of course there could be 2 electrons having opposite spins in this 1s orbital. And what we are essentially saying is that the energy of each of these 2 electrons is dependent upon this 1, which is basically the principal quantum number, and it depends on this s, which essentially means L is equal to 1, and it depends a bit on the spin quantum number, which also is called s. The spin quantum number can be either plus half or minus half, but this dependence upon the spin quantum number is not very great. In other words, what we are saying is that these 2 electrons, supposing that the 1s orbital is filled, so it has 2 electrons. These 2 electrons, their energy levels would be more or less the same. They would differ only slightly because the dependence upon the energy, the dependence of the energy upon the spin quantum number is very small. The energy levels of these 2 electrons in the 1s orbital can be plotted in this particular energy level diagram. So I would basically have 2 energy levels which are very, very close to each other, and if there are indeed 2 electrons in the 1s orbital, then there would be 1 electron corresponding to this energy and another electron corresponding to this energy. And in most diagrams, these 2 energy levels which are so close to each other are shown essentially as a single energy level, which corresponds to any of the 2 electrons in the 1s orbital. So for example, if the 1s orbital is completely filled, then you could graphically represent this as 2 electrons having the same energy, which corresponds to the energy level of the 1s orbital. Likewise, the energy level of any of the 2 electrons in the 2s orbital is shown as a single energy level, like this line, and I'll write 2s over here. And similarly, the other orbitals, that is the 2p orbital and the 3s orbital, are shown as single lines in the energy level diagram, and they are of course above the 2s level. Now the difference of course between the 2p line and the 3s line is that the 2p can accommodate 6 electrons and the 3s can accommodate only 2 electrons. The next thing now to consider is what happens to these individual energy levels when 2 of such atoms happen to be very close to each other. Let us imagine, for the sake of argument, that in each of these single atoms, when they were isolated from each other, there were present 2 electrons in the 1s orbital, which means that now there are totally 4 electrons in the 2 atoms in the 1s orbitals. One might imagine, for example, that in the new energy level diagram, the energy levels of 1s and 2s are identical to the corresponding energy levels for a single isolated atom. The only difference being that in the 1s energy level there are now 4 electrons instead of 2. Now this is not entirely true. The reason is that when these 2 atoms approach each other and when they come very close to each other, the electron wave functions corresponding to these 4 electrons, they actually overlap. Now what this means in simple language is that these 4 electrons now belong to both of the atoms, and Pauli's exclusion principle dictates that these electrons which belong to the same system cannot have the same quantum states. So to make the quantum numbers or the quantum states of these electrons dissimilar, the single energy level of the 1s orbital now splits into 2 somewhat close energy levels, and each of these 2 energy levels now accommodates 2 electrons. Please note that, for example, these 2 electrons, they do appear to have the same energy, but their energy will be slightly different because their spin quantum numbers are different. But those 2 energies are so close to each other that we show it as a single energy level. So essentially, by this splitting of the 1s energy level, no 2 of these 4 electrons can have the same quantum states. And in a similar manner, the 2s energy level splits into 2 somewhat close energy levels to fulfill the requirements of Pauli exclusion principle. So for example, if there were 2 electrons in the 2s orbital for each of the 2 atoms, then now there would be 4 electrons accommodated in 2 different energy levels, like that. The process has been carried forward in the next diagram, in which we show the energy levels corresponding to the electrons belonging to 6 atoms which are very close to each other. So you can see that the 1s energy level has split into 6 fairly close energy levels, and the 2s energy level has similarly split into 6 fairly close energy levels. And if all of these energy levels be occupied, then there will be 2 at every level, like that. And now finally you can imagine what happens when you pack millions of atoms close to each other like in a solid. The individual energy levels corresponding to 1s now split into so many individual energy levels which are so close to each other that essentially it appears to be a continuous band of energy, and so it's now called the 1s energy band instead of the 1s energy levels. And likewise the 2s energy levels split up into so many energy levels and they are so close to each other that it becomes the 2s energy band. And the difference between energy levels like this and an energy band like this is that an energy band is a continuous band of energy, whereas energy levels are discrete in nature. Up till now we have talked about energy bands in solids in a rather simplistic way, although the essence of what we have said still holds good. The situation in real life can be a bit more complex than the way that we have described. For example, we can consider a single atom of some solid and let this red line be the energy level corresponding to some orbital of that particular atom. Now, when millions and millions of such atoms come together to form a crystal, it is even possible that this single energy level gives rise to not one energy band but to two energy bands. One may be here and the second one may be here, which essentially means that an electron can have any energy in this range, and likewise it is allowed to have any energy in this range, but it is not allowed to have any energy whatsoever in this range. And the second odd thing that can happen in real life is that energy bands can actually overlap each other. So I'll show that in this same diagram. Let me just create some space over here. So this single energy level, as before, I've shown it as split into two energy bands. Now you can imagine that in the single atom there was another energy level which was somewhere over here below the red one, and imagine that this energy level also has split into two bands. Well, the simplest thing to draw would have been this. When the crystal forms, the wave functions overlap and you get energy bands like that. But something more complex than that can happen, namely that this energy level, when the crystal is formed, it splits into two bands. One of them, of course, I show like this. There's nothing unusual in that. And the second one, this is something unusual. It actually overlaps with one of the other energy bands. So as far as energy bands go, this is to be treated as a single band. So in this diagram you see three energy bands, and once again an electron is allowed to have any energy whatsoever within this band, and also within this entire band, and also within this entire band, but it is not allowed to have any energy whatsoever in the two energy gaps. So in this gap and in this gap. So that's a proper picture of what sometimes happens in real life when energy bands are formed, when millions of atoms collect to form a crystal. And of course the importance of knowing the exact energy bands of a solid is that such knowledge helps us to deduce or to conclude about the electrical property of that particular solid. And in particular in this chapter we will be using the notion of energy bands to understand why semiconductors behave in the way that they do. We shall first see how the energy bands of a solid directly influence its electrical conductivity. Supposing we apply a potential difference to a solid, like in this diagram. So you know that there will exist an electric field, let's call it E bar, in this direction inside the solid. And if the solid is a conductor of electricity, then it would start electrons flowing in the direction opposite to the field. So you will get an electron current flowing from right to left, which of course means that there is a conventional current I flowing from left to right in this particular body. However, not all electrons can contribute towards this electrical current. Whether a given electron can or cannot participate in the electrical current depends upon its position in the energy band diagram. To explain this, I have drawn or started to draw an energy band diagram. Note that the symbol E here stands for energy. It's not the electric field. And this red thing is some energy band. Now let's imagine that there is an electron in this solid which is energy wise situated at this point. So what it basically means is it is in this particular energy band, and its energy level corresponds to this much. Now if this particular electron is to participate in the electrical current, then it is necessary that there must be some vacant energy state immediately above its own energy. What I mean to say is there must be some energy state which is vacant in the vicinity of the energy of the electron, but above it, maybe over there, somewhere among these three energy states perhaps. This is because the electric field set up in the solid imparts a small additional energy to this electron, if of course this electron is going to participate in the conduction of current. So the electron tries to find a nearby higher energy level, and if it succeeds, so for example over here there are three energy levels which are nearby and higher, and maybe the electron can go to the first of them over there. So if it succeeds in going to a nearby higher energy level, then it takes part in the current. On the other hand, now we consider a scenario where there are no vacant energy levels immediately above the energy level of this particular electron. In that case, the electron cannot enter into any immediately higher energy level, and hence the electron is not in a position, or it is not allowed to gain energy from the electrical field, and hence the electron will not contribute towards the current. And this simple mechanism can be used to explain why certain solids are conductors of electricity, whereas some of them are insulators, and thirdly, why there are certain solids whose electrical characteristics lie somewhere in between conductors and insulators. Of course we are talking about semiconductors. So let's first consider the case of conductors. A good example to start with is that of sodium. Sodium is a metal, and all of us know that sodium is a good conductor of electricity, being a metal. A sodium atom, an isolated sodium atom which has 11 electrons, has an electronic configuration corresponding to 1s2, 2s2, 2p6 and 3s1. And the energy level diagram for an isolated sodium atom has been drawn over here. It's not drawn to scale, but there are going to be 4 energy levels in which electrons are present. So there will be 2 electrons over here in the 1s level, there will be 2 over here, 6 over here, and 1 over here. So what that essentially means is that the first 3 energy levels are completely filled, whereas the last, the 3s energy level, is half filled. Remember, the 3s orbital can accommodate 2 electrons, and in sodium there is only one 3s electron. So that makes the 3s energy level half filled. Now consider what happens when millions and millions of sodium atoms combine and form a sodium crystal. We can expect that because the sodium atoms are now very close to each other, the energy levels change into energy bands. So the 1s energy level, it becomes an energy band, which we can call the 1s energy band, like that. Note that because every sodium atom, its 1s orbital is completely filled, therefore the 1s energy band of the sodium crystal will be completely filled with electrons. There will be no vacancy in the 1s energy band. Likewise, there will be a 2s energy band corresponding to the 2s energy level and a 2p energy band corresponding to 2p. Now, for a similar reason as explained before, these two energy bands will also be completely filled. So we have drawn three energy bands, 1s, 2s and 2p, which are completely filled, which means that there is no vacancy present in these three bands. Now the situation is going to be different when it comes to the 3s energy band. It's going to be half filled, for the simple reason that to begin with, every sodium atom's 3s orbital was half filled. Now what this means in other words is, if there are n number of atoms which totally make up the crystal lattice, then of course there would be totally 2n allowed states in the 3s energy band. That is essentially because one atom has two allowed states, two allowed 3s states. So when the 3s energy levels combine to give you a 3s energy band, there are going to be 2n allowed states. However, every atom has only one electron in the 3s state, which would mean that when these n atoms come together to form a crystal, although there are 2n allowed states in 3s, they are occupied only, that is the 3s energy band is occupied only by n electrons, which once again means that the 3s energy band is half filled. And so when an electrical field is set up in a block of sodium, like that, so you know there's a field in this direction, and this field will try to move the electrons in the opposite direction from right to left. So when that happens, it is these electrons over here, they are present in the 3s energy band. These electrons can easily go to the immediately higher energy states which are available to them. In other words, they can go over here and over here and over here, and hence these electrons can participate in the electrical current. Note that the additional energy which they receive when they go into the higher state is in the form of the kinetic energy which they gain from the field. And so we know from all this discussion why sodium is a good conductor of electricity. Note that the electrons in the lower energy bands, that is 1s and 2s and 2p, do not contribute toward the current because they do not have nearby higher energy levels to enter. Although there are vacant states available in the half-filled 3s band, which means that theoretically an electron in the 2p band could go over here, or an electron in the 1s band could go over here theoretically. The additional energy which these electrons need from the field to go to that energy level is simply too high. Also note that the highest completely filled band in a solid is called the valence band, which would mean that for sodium the 2p energy band becomes the valence band, and the immediately next or the immediately higher band after the valence band is called the conduction band, which means that for a sodium crystal the 3s energy band becomes the conduction band. And obviously the name conduction band is because the electrons in this band give sodium its conductivity. Now we come to another way in which a conduction band can be generated, and this happens in some other metals, like for example in magnesium. A single magnesium atom has of course 12 electrons, and so the electronic configuration would be 1s2, 2s2, 2p6, 2s2, 2p6 and 3s2. And this of course means that the 3s energy level is completely filled in a magnesium atom. Remember, the 3s orbital can accommodate a maximum of 2 electrons, and so when millions and millions of magnesium atoms combine to give a magnesium crystal, the 3s energy band is going to be completely filled. So we now have to explain why, in spite of the apparently highest energy band in a magnesium crystal being completely filled, how come magnesium is a good conductor of electricity? The explanation lies in the fact that in a single magnesium atom the 3p orbital is completely vacant. Also remember, for energy levels to combine to give an energy band, it is not necessary for the energy levels to have electrons in the first place. They can even be vacant, like these 3p energy levels of the sodium atoms. And so when a magnesium crystal is formed, the 3p energy levels combine to give a 3p energy band, and this 3p energy band in magnesium has a peculiar characteristic. The 3p band in a magnesium crystal overlaps the 3s energy band. So what I mean to say is, for a single magnesium atom, if we draw the energy level diagram, so maybe I'll draw only the 3s energy level and the 3p energy level. So when the 3s energy levels combine to give a band, and likewise when the 3p energy levels give a 3p band, it so happens that these two bands, they overlap. So I can call it the combined 3s 3p energy band. It comes from this as well as this, and naturally there are going to be some filled states because the 3s energy levels are completely filled in their individual atoms. So these electrons are going to be there in the 3s 3p combined band. But remember, the 3p energy level is vacant in a single atom, so naturally there are going to be some vacancies too. And of course you know that the electrons will tend to occupy the lower energy states in the 3s 3p band, but when they are excited either by heat or electrically or otherwise, they can jump to the next higher band, or rather to the next higher energy level. In short, there are plenty of available vacant states over here for these electrons to move into, and hence magnesium, like sodium, is a good conductor of electricity. The next class of solids to consider is insulators. As you know, insulators are very poor conductors of electricity, and hence if you take an insulator and you apply a potential difference across it like this, then you get zero current or almost zero current. And the reason for this behavior of an insulator is once again found in the energy bands. As you know, the highest completely filled energy band in an insulator or in any material is called the valence band. So that's shown over here for an insulator in the energy level diagram. Remember, the bands which are below the valence band do not contribute very greatly to the electrical properties of the material, and so we don't consider them. Now, if you recall, the next higher energy state after the valence band is called the conduction band. So the conduction band in an insulator, I can schematically draw it like that. So basically that's the conduction band. And you may also recall that in metals, that is in conductors, the conduction band is partially filled with electrons. In contrast to this, in insulators, the conduction band is completely empty or vacant. So I'll just draw some electrons over here signifying the completely filled nature of the valence band, and in contrast the conduction band in an insulator is completely empty. Now recall that to participate in electricity conduction, an electron must move up in the energy band a little bit, because the electrical field provides it a little bit extra energy in the form of kinetic energy. And in this diagram, the only empty energy states which are available for an electron to move up are present in the conduction band, because the valence band, as you know, is completely filled, which means that for an insulator to conduct electricity, these electrons over here must move up into the conduction band, and the energy needed for them to move up is to be provided by the electric field which you apply to the insulator. However, the band gap between the valence band and the conduction band, that is this energy difference, in the case of an insulator is typically of the order of 5 to 10 electron volts. However, the energy which an electron can gain from a normal electric field, that is an electric field of normal magnitude, is quite small as compared to this band gap of 5 to 10 electron volts, and hence it is energy wise impossible for these electrons in the valence band to get excited by the electrical field and enter the conduction band. And since there is no way in which these electrons can gain energy from the applied electrical field, the electrons of an insulator cannot participate in the conduction of electrical current. And that's the reason why an insulator cannot conduct electrical current. The reason basically lies in the nature of the energy bands. Just to give you a practical example, diamond is a good example of an insulator, and the band gap of diamond is approximately equal to 6 electron volts. And it can be argued that in order to supply energy of 6 electron volts to an electron of diamond, the potential difference which is to be applied across, let us say, a 10 centimeter wide diamond slab, you are applying a potential difference this way and trying to get a current. The potential difference that you must apply is of the order of millions of volts, and this is clearly not practical. Now we also have to investigate the role played by thermal collisions in the process of electricity conduction. As you know, at room temperature, the ions of the lattice are constantly vibrating, and one of these valence band electrons can possibly gain some energy by colliding with such a vibrating ion or even with another electron. Now hypothetically, if the energy gained by the electron it is larger than or equal to the band gap, then the electron can actually be pushed up into the conduction band. So the electron may find itself in, let's say, this energy state after a thermal collision. And now clearly for this particular electron there are many vacant energy states available immediately above it. This electron can now participate in electrical conduction because it can gain the small amount of energy from the electrical field, because it can be pushed up into this state or maybe into this state which is slightly above the current state of the electron. In other words, this electron can gain energy from the applied electrical field and hence it can participate in electrical conduction. So if the thermal collisions are able to push these electrons up from the valence band into the conduction band, then we will see that the insulator becomes a good conductor of electricity. However, in practice, the additional energy which is gained by an electron due to such thermal collisions at room temperature is usually much smaller than the 5 to 10 electron volts band gap which is present in an insulator. Hence we see that at room temperature an insulator cannot become a good conductor of electricity even by the mechanism of thermal collisions. We can now go to the third category of solid materials in which we are particularly interested in this chapter, namely semiconductors. Semiconductors are materials which lie somewhere in between conductors and insulators as far as their electrical conductivity goes. Two of the most commonly used semiconductors are silicon and germanium. At very low temperatures, a semiconductor's energy band diagram is just like that of an insulator. So you would have a valence band which is completely filled with electrons, and above it you would have a conduction band which is completely empty. And that is why at very low temperatures, as far as the electrical conductivity goes, there is no difference between a semiconductor and an insulator. In other words, at very low temperatures, a semiconductor behaves like an insulator. It doesn't conduct electrical current. Now, the fundamental difference between a semiconductor and an insulator lies in the band gap between the conduction band and the valence band. We have already seen that in an insulator the band gap is of the order of 5 to 10 electron volts. In a semiconductor the band gap is much smaller. It is typically of the order of 1 electron volt. As an example, we can consider the case of silicon, where the band gap is roughly 1.1 electron volts. Now, because this band gap is small in a semiconductor, we see that at room temperature it is possible that a few electrons from the valence band can actually gain sufficient energy from thermal collisions to be pushed up into the conduction band, like that and like that. And this enables a semiconductor, when we apply a voltage across it, to conduct a small electric current in the direction of the electric field. At higher temperatures, more electrons in the valence band jump across the band gap, and as a result of this the material conducts electricity better. So we see that in a semiconductor, as the temperature rises, the resistivity, which I'll call rho, decreases. That's because the conductivity increases. Note that there are two factors which are at play over here. Firstly, the increase in the temperature increases the number of free electrons, as we have just now seen, and this causes a decrease in the electrical resistivity. Now the second factor actually goes against this. As the temperature rises, the vibrations of the ions in the crystal lattice, they increase, and this means that the number of collisions between the free electrons and the vibrating lattice ions also increases. So this makes it more difficult for the free electrons to get across the semiconductor, which basically means that the resistivity increases because of this factor. So when the temperature of a semiconductor rises, the resistivity tends to decrease because of one factor, but it tends to rise because of another factor. And it is seen that in semiconductors, the first factor tends to dominate the second factor. In other words, when the temperature rises in a semiconductor, the number of free electrons rises, and the decrease in the resistivity because of that tends to dominate the increase in the resistivity because of the increased number of collisions. The net effect of this is that in a semiconductor, when the temperature rises, the resistivity falls. So it becomes a better conductor of electricity at higher temperatures. Indeed, if we want to test whether a given material is a semiconductor or not, we can check if its resistivity falls when we increase its temperature. We have seen how the presence of free electrons in the conduction band enables a semiconductor to conduct electric current. But in reality, there is one more important mechanism involved when current flows through a semiconductor. In this section, we shall study that there are two mechanisms by which current can be conducted in a semiconductor. The first one is by the electrons, and the second is by what is known as holes. We have seen earlier that only if an energy band is partially filled can the electrons in that energy band contribute towards the material's electrical conductivity. We have also seen earlier that at low temperatures the valence band in a semiconductor is completely filled with electrons and the conduction band is completely empty. That is why the electrons in the valence band cannot participate in electrical conduction of current, and also there are no electrons present in the conduction band to contribute towards the current. So we have seen that at low temperatures this is the reason why a semiconductor behaves like an insulator. Now at higher temperatures, like at room temperature, some of the electrons from the valence band of the semiconductor migrate to the conduction band. For example, let's say this electron goes over here, and maybe this electron goes over here, and one third example, let's say that this electron, it goes over here. Now when this happens, these electrons which have migrated to the conduction band leave behind vacant energy states in the valence band. So for example, there would be a vacant energy state over here, another vacancy over here, and a third vacant energy state over here. Now because of this, we see that not only is the conduction band partially filled with electrons, and hence it can participate in electrical current conduction. But the valence band also is partially filled, which means that the remaining electrons in the valence band can also contribute towards the electrical conductivity of the material. This is because the valence band electrons now have some empty energy states to jump up to after gaining energy from any applied electric field, and hence these electrons can also contribute towards the electrical current. So when a potential difference is applied across a semiconductor like that, the few electrons which have migrated to the conduction band move against the electric field as expected. So you know that the electric field in this case is from left to right, and that would mean that the conduction band electrons would move from right to left. And similarly, electrons in the valence band also try to move in a similar manner, that is from right to left, like that, and a few of them actually succeed in doing so by occupying the vacant states in the valence band. These two mechanisms of current conduction in a semiconductor are easily understood from the physical diagram of a pure silicon lattice. So you are aware that silicon is the most popular or the most widely known semiconductor. Now in a silicon crystal, each silicon atom has 4 electrons. It contributes 4 of its electrons to the valence band. In other words, each silicon atom has 4 valence electrons of its own. The valency of silicon in this lattice is 4. Now in a silicon crystal, each silicon atom is covalently bonded with 4 of its neighboring atoms, and we can even draw the schematic diagram of a silicon lattice at low temperature as follows. So to begin with, we draw the silicon atoms. Remember, this is a 2-dimensional representation of what ought to be a 3-dimensional lattice. So it's a schematic diagram, and between any two neighbors there is a covalent bond. So I'll just show the covalent bond. I'm showing it by these 2 lines. It's a single covalent bond. I'm just showing it by 2 lines, and the reason of course is I want to show the electrons which are shared. So one of the electrons is here and the other shared electron is over here. It's a single covalent bond between these 2 neighbors, and likewise I've got another single covalent bond between these 2, another covalent bond here, another covalent bond here. So I'm showing a single covalent bond by 2 lines, unlike in chemistry where I believe you show a single line. It is just because I want to show 2 electrons. So let's put in the electrons, the 2 shared electrons here, here and here. So you can see in this schematic diagram that this particular silicon atom, it actually has 8 electrons, and that satisfies its valency. Of course, the 8 electrons, out of them 4 are contributed by itself and 4 are coming from its neighbors. So these are essentially 8 shared electrons. Now we can draw the rest of the electrons and the bonds in a similar way, like this. So once again, every silicon atom is surrounded by 8 valence electrons, 4 of which are contributed by its neighbors and 4 by itself, and hence the valency of 4 of every silicon atom is satisfied. Now we have said that this is the lattice diagram at low temperatures. So at low temperatures, what happens is these valence electrons are strongly bound to their atoms. They are strongly bound to their atoms, and hence they cannot move from the locations, from their own locations, when we apply an electric field, the bonding between them and their atoms is simply too strong. And that's why when you apply a potential difference to a silicon crystal which is at a low temperature, then you get a current of 0. Silicon acts like an insulator at low temperatures. But as discussed earlier, at higher temperatures, like for example at room temperature, some of the valence band electrons get pushed up into the conduction band. So what would it mean in the lattice diagram? In the lattice diagram, it would mean that some of these valence electrons or valence band electrons, some of these get separated from their parent atoms, and after this separation they would be free to roam about inside the crystal. They are thus able to contribute to an electric current when a potential difference is applied. So let's now try to draw the schematic diagram of the silicon lattice at room temperature. So what you will see is some of these electrons are no longer in their original places. Maybe this electron, it's roaming about somewhere in the crystal. I'll just draw it over here for convenience, and over here I'll just draw an empty circle, which means that it's a vacancy. The electron was in that place and now there's nothing there. Likewise, maybe a few more electrons we can show as having left their original positions. So that one, it leaves an empty spot over here and it's roaming about somewhere in the crystal, but for convenience I'll just draw it close to its parent atom. It need not actually be there. And a few more, maybe this one, and maybe this one, and maybe this one. So you can see that each free electron which is liberated from its parent atom leaves a vacancy in its place. Thus, although most of the covalent bonds in the lattice have 2 electrons, so for example this covalent bond has 2 electrons and most of them do like that. Now that's of course expected, that's the normal behavior, but some of them will have a single electron. So you can see this one for example, and in place of the second expected electron you will get, or you will see, an empty position which has been vacated by an electron which is now free. Now each of these vacant positions, this one, and so on, is generated by the absence of a negatively charged electron. The electron which was there has gone away, so it's absent, and hence this empty position is now associated with an effective positive charge, and that of course follows from the principle of superposition in electrical fields or in electricity. So you can effectively assume that these vacant positions, these are the other ones, they have a positive charge, and these positively charged vacancies in the lattice are given a name. They are called holes, very appropriately, because they stand for the absence of electrons. Now let's imagine that at room temperature you apply a potential difference to a silicon crystal like that. So you know of course that the field, electric field E bar, is from left to right, so it will tend to carry positive charge from left to right or negative charge from right to left. So as discussed earlier, the free electrons, now we are talking about these electrons in this picture, so these electrons over here which are liberated from their parent atoms, these are the free electrons, and in the energy diagram these are the ones that have gone to the conduction band. So these free electrons, as discussed earlier, move from right to left, contributing towards an electric current from left to right. So this current contribution comes from the free electrons in the conduction band. But in addition to this, we can also get the valence electrons moving from right to left and contributing to the electrical current from left to right. So I'll explain this in the diagram, but you need to know at this stage that this contribution towards the electric current, it's coming from the valence electrons, and the first contribution is from the free electrons. And the motion of these valence electrons, that happens by occupying the holes. Now what do I mean by that? Let's go to the lattice diagram and look at it from that viewpoint, from the what happens physically. So just imagine that this lattice diagram corresponds to the right hand side picture where the electrical field is from left to right. So I'll just show the field. It's trying to push electrons in the opposite direction, that is in that direction, and there's no doubt about the conduction electrons or the free electrons like these are going to move actually from right to left. So what do I mean when I say that the valence electrons can also move from right to left? It's because they have vacant positions to occupy. So for example, let's take a look at this electron. You can see that there is a space to the left of it which it can occupy. It wants to go towards the left. The field is trying to push it towards the left. So you can imagine that this electron, it actually occupies, it shifts towards the left, and of course it leaves a gap over here like that. So a valence electron has gone towards the left. Now what else can happen, or what can happen next? Maybe this valence electron, it sees the hole over here, and it's possible that it can occupy that position. So it moves over here, and what happens is the hole now shifts towards the right. So that's very important to understand. If a valence electron moves into a hole, then the hole moves into the old position of the valence electron. It moves in the opposite direction, something like that. So you can see that the hole has moved from this position to this position to this position, and the valence electrons, they are basically moving from right to left. So the valence electron which was over here, it went here, and the valence electron which was over here, it moved over here. So we note that it is the presence of these vacancies, what we have called holes, which causes the valence band electrons to contribute towards the electrical current. Now conventionally, the current due to the valence band is viewed as the motion of the positive holes moving in the direction of the field. So what I mean is, really speaking, what's happening is the valence electrons are moving in this direction. I just showed that to you, how the valence electron moves. But it is a convention to assume that instead of these negatively charged valence electrons moving from right to left, that is against the field, the convention is to assume that the positively charged hole, you assume that the hole is a carrier of positive charge. It moves, or these holes move with the field, that is in this diagram, from left to right. So now in this right hand side diagram, I can change the direction of this arrow, which was the contribution towards the current from the valence electrons. So I can now say that there are holes which contribute towards the current, and they move from left to right with the field. And so in a nutshell, the electric current in a semiconductor has two components. Number one, the free electrons which are negatively charged moving against the field, and the holes which are positively charged moving with the field. Now there is one last term that you should know. Every time a valence band electron enters the conduction band and becomes a free electron, it also leaves a corresponding hole in the valence band, and this pair is called an electron hole pair, or EHP in short. Now when we talk about pairs, the implication is the number of free electrons is going to be equal to the number of holes, and that's obvious because the silicon lattice or the silicon crystal as a whole is electrically neutral, and therefore the number of negative free electrons must equal the number of holes, which are of course positively charged. We have just seen how a pure semiconductor, which is also called an intrinsic semiconductor like pure silicon, can conduct electricity at room temperature. However, the conductivity of a typical intrinsic semiconductor at room temperature is quite small. This is because the number of electron hole pairs generated by thermal collisions is quite small at room temperature. The conductivity of an intrinsic semiconductor can be greatly increased by introducing a tiny amount of impurity into the crystal structure. This process is called doping the semiconductor, and the impurity thus introduced is called the dopant. Typically, the ratio of dopant atoms to semiconductor atoms in the lattice is 1 dopant atom for every 10 raised to 6 or 10 raised to 7 semiconductor atoms. This tells you how tiny the amount of dopant introduced actually is. A semiconductor in which a dopant has been introduced is called an extrinsic semiconductor. Now, there are two types of dopants or impurities which are possible. One is called an N-type impurity or N-type dopant, and the second is P-type. And to understand how these dopants act, let's take the example of a silicon crystal, and let's consider first a silicon crystal having an N-type dopant. Recall that in an intrinsic or a pure silicon crystal, each silicon atom is surrounded by 4 other silicon atoms, and it forms covalent bonds with each of these 4 neighbors. At low temperatures, each covalent bond has 2 valence electrons, like this, or like this, or like this. But at room temperature, a small number of electron hole pairs are formed by some valence electrons escaping from the parent atom. So you can see electron hole pairs here, another one is over here, another one is over here, and so on. These electron hole pairs can roam about in the crystal freely, thus increasing the conductivity of the crystal. Consider now that any element from the 5th group of the periodic table, like for example phosphorus or arsenic, is introduced in the silicon lattice in tiny amounts. This type of impurity is called an N-type impurity or an N-type dopant. Now in this example, we will assume that the impurity which we use is phosphorus. And further, for a better understanding of the mechanisms involved, let us assume that there are no electron hole pairs which are thermally generated. So it's just to understand how the n-type dopant acts. Later on we can reintroduce these electron hole pairs. So this electron is going to go back into its original position, and so is this, and so is this. So the picture now is like this. So I believe that now I've put everything back in its place. And now the impurity that we use, we have assumed it's phosphorus. So it so happens that in the figure some of the silicon atoms get replaced by phosphorus atoms. So for example, we are going to assume that this particular silicon atom is no longer silicon, but it's phosphorus. And I'll show one more, maybe over here. This one is no longer silicon, it's phosphorus. So the red ones I have shown are silicon, the two blue atoms I have shown are phosphorus, the black dots are of course electrons. Now of course I have left out something in the figure. You all recall that a phosphorus atom actually has 5 electrons in its valence shell, whereas silicon has 4 electrons. So when I replace a silicon atom with a phosphorus atom, then of course I have one extra valence electron. So I will now proceed to show that extra electron associated with every phosphorus atom. It's the 5th electron of phosphorus. So this is one electron associated with this particular atom, and likewise for the other phosphorus atom I can show the 5th electron over here. So just to make things clear, if you look at this particular phosphorus atom, then you notice that there are 8 electrons around it which are involved in covalent bonds, and 4 of them have been contributed by the phosphorus atom. So we require the 5th electron to be shown, and it is this one. One way to view this situation is that there are phosphorus atoms which are pretending to be silicon atoms, and for that reason this electron, the 5th electron, the 5th valence electron of phosphorus, and likewise this is the 5th valence electron of the other phosphorus atom, these should not really be attached to the phosphorus atom. And in physics terms it means that the 5th electron of each phosphorus atom, the 5th valence electron, is relatively loosely bound to the parent atom, which means that this 5th electron can easily escape the parent atom due to thermal collisions, and it can roam about the lattice as a free electron. So just to make the point clear, I am going to remove this electron. It's no longer bound to phosphorus, and I'm going to put it somewhere else. It could be anywhere in the crystal. So just for the sake of the example, I'll put it over here, far enough from the parent phosphorus atom. Now you should note that before it got liberated, this particular electron, it did not belong to any bond between the phosphorus and the silicon atoms. So to make the point clear, you look at this electron. Although it is still attached loosely to its parent phosphorus atom, it's not taking part in any sort of bond formation between phosphorus and silicon. So let me now liberate this particular electron. Imagine that because of the temperature it gains sufficient energy to move away, and once it is free it can be anywhere in the lattice. So I'll just draw it somewhere over here. This is the free electron. So the electron can be visualized to have moved from this location to this location, and now of course it's free to move anywhere it wants, like that. in the silicon lattice or in the extrinsic silicon lattice. Now it's not intrinsic, since it's impure, it's called extrinsic silicon. When mixed with an impurity like phosphorus becomes extrinsic. And the point to be noted is that when this particular electron freed itself from its parent phosphorus atom, it did not create a vacancy in which a neighboring valence electron can slip into. To make myself clear, imagine that this electron which participates in bond formation, let's imagine that because of the temperature the electron is liberated. It goes over here, it's a free electron. Now in its original position there is a vacancy into which a neighboring valence electron can slip, and such a vacancy is called a hole. So a hole will be basically a vacancy or a vacant position in a bond, and you can see that when this electron was liberated, it did not create such a vacancy, and so the liberation of that electron did not create a place or a space for a nearby valence electron to enter. This means that unlike in electron hole pairs which we have talked of earlier, the liberation of this type of electron is not accompanied by the generation of a corresponding hole. Now the lattice is electrically neutral, and of course we do know that when the electron which was over here, it got liberated, and now let's say it has gone over here, we know that for the purposes of maintenance of charge neutrality, the removal of this electron from the phosphorus atom does mean that you can assume that a net positive charge does exist at that point, and of course effectively that neutralizes the negative charge carried by the electron which has now gone away. But this positive charge is not a hole. In fact, this positive charge is fixed to the phosphorus atom, which means that it's no longer a phosphorus atom, but it is a phosphorus ion with a positive charge, and this positive charge is not mobile like a hole, and it cannot contribute to the electric current. Since the positive charge is attached permanently to the phosphorus ion, I'll just put a plus sign inside the phosphorus, and likewise a plus sign over here. Now such a type of semiconductor which is doped with an n-type impurity is called an n-type semiconductor, and the impurity atoms are called donor atoms. For obvious reasons, each impurity atom, in this case each phosphorus atom, donates one free electron to the lattice. Now at room temperature, an n-type semiconductor will have three types of free charge carriers which are going to partake in the electrical conduction or electrical conductivity properties. So the first two types of charge carriers would be electrons and holes, which basically are electron hole pairs which are generated because of thermal collisions. Now these we have talked about earlier, but we have not shown them in the diagram, so maybe we can add a few of these electron hole pairs. We'll add one of them. So let's imagine that this particular electron, because of the temperature, it just goes away from the bond, so it leaves behind a hole, a positively charged hole, and the corresponding electron is somewhere in the lattice. I'll just show it for convenience over here. So this is an electron hole pair which is generated because of thermal collisions, and the electron as well as the hole are mobile. So if I apply a potential difference to the crystal, then both of them will contribute towards the current. And of course the third type of free charge carrier is the electrons which have been contributed by the n-type impurity. So of course we are talking about this electron which escapes from the phosphorus ion, and likewise we are talking about this electron. So these are free electrons, they don't have any corresponding holes, and that's the third type of free charge carriers. Now usually it is seen that these electrons generated, that is released by the phosphorus atoms, they greatly outnumber the electron hole pairs which are generated by thermal processes. So most of the current which we see in an n-type semiconductor when a potential difference is applied, most of that comes from the liberated fifth electrons which are provided by the n-type impurity like phosphorus. And lastly, in an n-type semiconductor, since the number of electrons is much larger than the number of holes, remember the number of electrons would come from two sources. Most of them are type number 3, a few of them are coming from type number 1, but in any case the number of electrons is much larger than the number of holes, and that's why in an n-type semiconductor free electrons or conduction band electrons are called the majority charge carriers, while the holes, because they are so small in number relatively, are called the minority charge carriers. And lastly, if you compare intrinsic silicon, a lattice made of intrinsic silicon, with a lattice made of extrinsic silicon, and let's assume that it is an n-type silicon lattice, then at the same temperature you would generally see that the extrinsic silicon, n-type silicon, would have much larger conductivity as compared to the intrinsic silicon, and that's because there are so many of these free electrons which the extrinsic n-type silicon possesses. We can similarly dope a silicon crystal with an element from group 3 of the periodic table like indium, boron or aluminium. These dopants are called p-type impurities, and each one of them has 3 electrons in the valence shell. Let us consider the example of a silicon crystal which has been doped with boron. We can picture the situation when the boron dopant atoms have replaced some of the silicon atoms in the crystal lattice. So you can see in this picture the blue discs which I have shown, these are the boron atoms, the red ones are silicon, and the black dots are electrons. And like before, I have assumed for simplicity that none of the valence band electrons has gone into the conduction band. In other words, in the diagram shown, there are no free electrons and no holes. This is of course just to understand how exactly a p-type impurity works. Now of course you will realize that in this picture there is one thing which is wrong, and we will now rectify that. Each boron atom has 3 valence electrons, not 4. So one of these I am going to rub out, and likewise I am going to rub out one of these electrons. So you can see that in actuality, since boron has 3 valence electrons, it forms covalent bonds with only 3 of its silicon neighbors. So what I mean is the following: this is a covalent bond between boron and silicon, and one electron has come from boron, the other from silicon. Similarly, this these two electrons, they participate in a covalent bond between boron and silicon, and similarly this pair of electrons. Now over here, of course, the covalent bond is not really formed because there is only a single electron coming from silicon. Now it so happens that to hold the boron atom securely in its place in the lattice, a valence electron from a silicon atom in the vicinity of the boron atom migrates to the boron atom. So for example, this electron, it migrates over here, it fits into this place exactly like that, and of course it leaves a vacancy in its original position. So you can see now that we have a situation where boron is now covalently bonded with all four of its silicon neighbors, and the process has also generated a hole, a positively charged hole, which is mobile, which means it can move freely in the lattice and hence contribute towards the electrical current. Another byproduct of this process is a negatively charged boron ion. Remember, boron was initially neutral, and it has got now an extra electron from the lattice, which makes it negatively charged. The semiconductor is now called a p-type semiconductor, and at room temperature a p-type semiconductor will have, number one, freely moving holes, and these come from the process which we have just described, I mean the process involving the dopant. And number two, the p-type semiconductor at room temperature will also have an equal number of fixed negatively charged boron ions. That is, the number of boron ions will be equal to the number of these holes. Of course, that's a requirement of charge neutrality. And what's more, these negatively charged boron ions, they are ions which cannot participate in current conduction, because although they carry charge, they are fixed. The charge is fixed to the boron ion, it's not mobile. And of course, at room temperature, the p-type semiconductor will also have electron hole pairs which have been generated by thermal processes which have been described earlier. So again, these electron hole pairs are mobile, they can contribute towards the current, and so can these. But usually the number of these holes, these, is much larger than the number of electron hole pairs. And that's the reason why in a p-type semiconductor the holes become the majority charge carriers, while the free electrons become the minority charge carriers. And at room temperature, the conductivity of p-type silicon or a p-type semiconductor is much larger than that of the corresponding intrinsic semiconductor, and the reason, of course, is because of the large number of these holes. Now these p-type impurities which we talked about, they are also called acceptor impurities. Like for example, boron over here is an acceptor impurity because it has accepted an electron to become a negatively charged ion. So just to complete the picture, I think I've left some things out in the picture. This over here is actually a negatively charged boron ion, so I'll just put a minus sign inside. And of course the reason why it's negatively charged is that it has accepted this extra electron from the lattice. and maybe some other things I can complete over here. This electron, I can imagine that it goes over here, it fits into this, so now it belongs to the bond between boron and silicon, and that would of course leave a mobile positively charged hole over here. And some other things in the diagram, maybe I'll show an electron over here, somehow it got rubbed out or I just missed it, right? So this is more or less the complete picture, excepting for one more thing, namely I have to still show a few electron hole pairs which have been generated by thermal processes. So I'll just show one of them. It's just to show you that that happened. So maybe I can rub out this electron, and the electron is now free. It has been liberated because of thermal collisions, and it leaves a hole which is also mobile. So that's an electron hole pair which has been generated by thermal processes. So this is more or less the complete picture of a p-type semiconductor at room temperature. And finally, there is one last process which needs to be described, and that's the process of recombination of electron hole pairs. So it happens when a free electron and a hole collide with each other. They neutralize each other, and in the process an electron hole pair gets destroyed. So for example, let's imagine that this free electron, it comes in the vicinity of some hole over here, so it just fits into that place, and now you have lost one mobile electron and one mobile hole. So that's called recombination, and this recombination process occurs simultaneously with the thermal generation of electron hole pairs, which we described earlier, the process by which this electron goes out into the lattice as a free electron and it leaves behind a hole in its place. So basically the recombination of electron hole pairs and the generation of electron hole pairs, they are opposite processes, they take place simultaneously, and at equilibrium the rate of generation of electron hole pairs equals the rate of recombination.